Hello. In this video, I'd like to discuss the main points in WilliamChan and colleagues' paper, Listen, Attend, and Spell, a neural network for large vocabulary conversational speech recognition. This paper introduces an end-to-end model for speech recognition which uses attention mechanism as well. The proposed model is an important milestone in speech recognition. Here are the chapters of this video, and in each of them, we will review a part of this paper. Speech recognition. Speech recognition is the ability for a machine or program to identify words spoken aloud and convert them into readable text. Before the rise of deep learning, state-of-the-art speech recognizers were complex systems that included acoustic models, language models, pronunciation models, and text normalization, among other elements. The main drawback of these models was that each of these components make assumptions about the underlying probability distributions they model. For example, n-gram language models and hidden Markov models make strong Markovian independence assumptions between words or symbols in a sequence. End-to-end training of such models tries to solve these issues by training all of the components at the same time. Acoustic models are updated in these models, but grammar and language models are rarely, if ever, modified. Listen, Attend, and Spell is a neural model that learns to transcribe an audio sequence signal to a word sequence, one character at a time, without the use of specific language models, grammar models, HMMs, or other methods. Model details. As the name of paper suggests, this model consists of three parts: listen, attend, and spell. Generally, we start from the log-mil spectral features and map to letters, although it's also possible to map to word pieces. The input is a set of T acoustic feature vectors, one vector per 10 millisecond frame, containing 40-dimensional log-mil filter bank. The listener is an acoustic model encoder that performs the listen operation. The listen operation reduces the length of the initial signal X by converting it to a high-level representation. In a speech recognition model, we want to map very long acoustic feature sequences to much shorter sequences of letters or words. A single word might be 5 letters long, but supposing it lasts about 2 seconds, would take 200 acoustic frames of 10 milliseconds each. Because this length difference is so extreme for speech, encoder-decoder architectures for speech need to have a special compression stage that shortens the acoustic feature sequence. A bidirectional long short-term memory RNN with a pyramidal structure, or PBLSTM for short, is used in the listen operation. We can reduce the time resolution by a factor of 2 in each successive stacked PBLSTM layer. The model described in this paper has 3 layers of 512 PBLSTM nodes on top of the bottom BLSTM layer to reduce the time resolution 8 times. This allows the attention model to extract the relevant information from a smaller number of time steps. The listen operation transforms the original signal X into a high-level representation H that has a much shorter length. Then, this vector will be passed on to the next part of the model, which is the attention mechanism. At each decoder time step I, the energy score, which is a scalar, is computed for each time step U, using vector HU, which represents time step U of H, and SI, which is the contents of the decoder hidden state. Here, both phi and psi are MLP networks. The scalar energy score is then converted into a probability distribution over time steps, or as we call it, attention weight, using a softmax function. The softmax probabilities are used as mixing weights for blending the listener features HU to the context vector CI for output time step I. The last stage is the spelling part. The spell function used a two-layer LSTM with 512 nodes each. In order to produce the transcription of the input audio, the context vector is fed into a LSTM network along with the previous hidden states and previous outputs. During inference, we want to find the most likely character sequence given the input acoustics. In order to do so, we use beam search. Here is how it works. Beam search has a hyperparameter named beam size. In this slide, the beam size is 2. So at time step 1, we select 2 tokens with the highest conditional probabilities. Each of them will be the first token of 2 candidate output sequences, respectively. At each subsequent time step, based on the 2 candidate output sequences at the previous time step, we continue to select 2 candidate output sequences with the highest conditional probabilities from all possible choices until a certain condition is met by the candidates. In this paper, authors have used beam size 32. It is possible to apply language models trained on large external text corpora alone, similar to conventional speech systems. But authors of this paper simply rescored their beams with the language model by combining it with a language model probability. Also, since they found out that their model has a small bias for shorter utterances, they normalized their probabilities by the number of characters. Results. For their experiments, the authors used a dataset of anonymized and hand-transcribed Google voice search utterances. This dataset contains data from 3 million searches, representing 2,000 hours of data. They also increased this amount by augmenting data using a room simulator, adding different types of noise and reverberations, which increased the amount of audio data by 20 times. Approximately 10 hours of utterances were randomly selected as a held-out validation set. A separate set of 22K utterances representing approximately 16 hours of data were used as the test data. Asynchronous stochastic gradient descent was used for training the model with learning rate of 0.2. The state-of-the-art model on Google Voice Search dataset is a convolutional long short-term memory fully connected deep neural network or CLDNN proposed by Sinath and colleagues, which achieved a word error rate of 8% on the clean test and 8.9% on the noisy test set. The listen, attend, and spell model achieved 14.1% word error rate on the clean test set and 16.5% error rate on the noisy test set without any dictionary or language models. Language model rescoring improved the results for the clean and noisy test sets to 10.3% and 12% respectively. Like the other papers with attention mechanisms, a visualization of attention weights may better describe what the model really perceives under the hood. As we can see in this slide, the content-based attention mechanism creates an explicit alignment between the characters and audio signal. This figure visualizes the attention alignment between the characters and the filter banks for the utterance, "How much would a woodchuck chuck?" As you can see, attention weights are similar for words with acoustic similarities. Conclusion. A neural speech recognizer was presented in this paper, which can directly transcribe acoustic signals to characters without using any of the traditional elements of a speech recognition system, such as HMMs, language models, or pronunciation dictionaries. Thanks for watching. I hope you find this video educational and informative. If you liked this video, please subscribe to my channel. See you in the next video.